There is grandeur in this view of life.
Welcome to Evolution Talk with Rick Coast, an introduction to the oldest story ever told.
How do you do? We are about to unfold the story of Frankenstein, a man of science who sought to create a man after his own image without reckoning upon God.
In the 1931 film Frankenstein, science created a monster it couldn't destroy. And that was the actual tagline of the movie. To give credit where credit is due, it was Victor Frankenstein who created the creature. But before he could reanimate the lump of dead flesh he had put together, he first had to give his creation a brain. Without it, his monster would never have left the laboratory table, nor entered our collective consciousness. Brains are, after all, pretty important. Now, have you ever wondered about your brain? Science didn't provide you with a brain. Nobody did. Yet it's there. So, exactly how did it come to be? What evolutionary forces swept in to form your brain? Now, it's fair to say that it didn't happen overnight. But before we start wondering how it is that we have the sort of brain we have, let's first look at how it started. What small little collection of synaptic proteins served as the base structure? For this, we can look at the sea sponge. I bet you never thought you had anything in common with a sea sponge. Yet you do. We share a common ancestor with them, although a very distant common ancestor. The thing with sponges is that they don't have a brain or a central nervous system. What they are is a collection of cells. When multicellularity became a thing, the sponges were among the first to give it a shot. Now, in order for their cells to communicate with one another, they use proteins. So it's not a stretch to see how this method of cellular communication might have evolved for the cells to band together for protection, using proteins to communicate. And chemical messages pass from cell to cell, binding the entire group together. It's not that much different from the way the neurons of your brain communicate with one another. So imagine this. Imagine an organism, an early organism that consists of billions of cells that's able to communicate in order to avoid predation. Or, on the flip side, a group of cells that is able to direct itself towards another group of cells with the goal of predation. Now, to do so, to move in a certain direction, you must first have a sense of direction. If you're an amorphous blob of cells, who's to say which way is up or which way is down? You're just floating along hoping to bump into something you can assimilate. But what if some of these cells become sensitive to light? This collection of cells could communicate to the rest of the colony to move towards or away from a light source. As these cells become more specialized, they remain grouped together. You can think of them as the leaders of the pack. When they want to move this way, they communicate back to the rest of the colony to move. I say back because these cells are now in the front. They dictate the direction in which the colony, we may as well call it an organism, which direction it moves. Now, over billions of years, this region, the specialized cell region, begins to develop sensory organs. Those light-sensitive cells slowly develop into eyes, and another organ begins to develop. A centralized structure of highly specialized cells that control everything. A command center that receives information and passes it along. As time goes by, these organisms become more and more complex. They had to in order to survive. As cells changed and mutated, those changes that were of a benefit persisted. It was trial and error on a grand scale, and one of the most important, if not the most important adaptations was this little group of highly specialized cells. As the organism grew more complex, there was a lot more for these cells to do. Their jobs became more demanding, especially when the organism began to move away from the environment it had spent its first few billion years in, and moved on to dry land. And these cells were responsible for regulating things such as breathing, basic motor skills, and controlling the heart. Now, if nature was Dr. Frankenstein, then this specialized cell region was an early beta version of our brain, a 570 million year old beta version. We can now refer to it as the hindbrain. It's still there, buried beneath everything else that is developed to become your brain today. It's responsible for many of your basic motor behaviors and movements, just like it was 570 million years ago. Your medulla, pons, and cerebellum are found here. This all worked pretty well for a while. But of course, nature isn't content to leave things alone. It has to keep tinkering, especially when it comes to keeping the organism competitive. So around 250 million years after the development of the hindbrain, more specialized structures began to appear. Now, these were built upon the pre-existing hindbrain to deal with the fact that it's a dog-eat-dog world out there. This region, the one built upon the hindbrain, is now called the limbic region, and it's responsible for more complex behaviors such as fighting, emotions, and behaviors which promote or facilitate reproduction. Reproduction is, after all, what it's all about. Nature wasn't done yet, though. Now that the organism could take care of its basic needs, or basic survival needs, it was time to give it something to think about. It was time to create your neocortex. I'm going to leave Dr. Frankenstein behind now and move on to another analogy to help us along. Now think of a city, or how a city develops. First, you start with a few dirt roads and perhaps some simple shelters. These represent your hindbrain. Your basic needs are met here. You have shelter and a direction. The dirt road tells you where to go and how to get home. Then, over time, as more and more people find their way to your little town, other structures begin to emerge to suit the town's needs. Maybe there's a little store and a barber shop and a saloon. Even a sheriff's office. You can call these additions to the town the limbic region. There's a lot more activity, more conflict, and even conflict resolution going on now. But then, more people move in. Some of the roads are expanded, and new structures begin to emerge. Tall structures which dominate the sky. Skyscrapers appear almost overnight, as well as banks, insurance companies, art galleries, and air control towers. Now this is your neocortex, the most specialized area of all. It took a long time to get here, but now that it's here, there's no going back. If you look closely, everything that came before is still there. You can still see those first dirt roads, although they've been paved over by now, and the barbershop and saloon are still there under different management. Even the sheriff's office is there, but now a large federal building sits above it. What was once one floor is now 10. Without your neocortex, you wouldn't be able to talk, paint, think, or do any of the higher cognitive things that you can do. You'd still be scurrying around the trees hoping to avoid being eaten. Now you're able to sit 20 floors above it all and raise a toast. You've come a long way. So now that we have some idea as to the order of things, how nature built your brain over time, there's a question to be asked. Maybe you've already asked it. How did it expand so quickly? And granted, a few million years doesn't sound fast when you say it out loud, but considering your hindbrain first appeared 500 million years ago, your neocortex underwent a rapid expansion 2 to 3 million years ago, much faster than the mammals you share the planet with. So let's think about it for a moment. It's not like it happened overnight, right? Something must have accounted for it. Something in the environment that presented enough challenges to shape your brain into the formidable force it is today, evolutionarily speaking, of course. It's not like we have reached the apex of brain development, nor does it mean it couldn't have happened an entirely different way. We could have spent the last 2 to 3 million years with small brains. We started out with small brains. But you have to remember, we shared this planet with the dinosaurs at one time. Well, when I say we, I mean our mammalian ancestors did. They scurried about under tree limbs and the underbrush to keep out of sight. Those were challenging times for sure. Our ancestors had to be keen and they had to be cunning. They also needed well-developed senses. But larger brains would help with that. As our eyesight got better, so too would our neocortex. But then, as luck would have it, the dinosaurs died and the mammals inherited the earth. And that was 65 million years ago, roughly. After that, it was time for mammals to rise up to take their place at the head of the table. Flash forward some 60 million years, and that's when we last shared a common ancestor with the chimpanzee. That was 5 to 6 million years ago. Their ancestor went one way and ours went the other. The Homo genus continued to evolve, travel to Europe, and spread. We didn't do this alone. We did it together in groups. Group dynamics takes a lot of energy to sift through. You have to remember things. You have to communicate. You have to face life together as a cohesive unit. And that takes computing power, and quite a lot of it.
The social brain hypothesis, as it's known, an explanation for why primates have very large brains. The argument is they live in very complex social systems.
That's British anthropologist Robin Dunbar during a talk he gave for the RSA in 2014. A large part of his work is in looking at the effects social groups had and continues to have on our growth as a species.
Now, in terms of how primates create their social relationships, it's actually a two-process mechanism. Part of it involves grooming here. Produces a massive release of endorphins in the brain. Endorphins are part of the pain control system. But then they give you this kind of opiate-like lightheadedness and all's well with the world, and you feel very warm towards those you're doing whatever with. And that, in a sense, sets up a kind of psychopharmacological platform of which the second component, which is the cognitive component, can then be built. And that's where the social brain bit comes in, and what it's doing is essentially allowing you to build up relationships of reciprocity and obligation and trust and so on. And in doing so, you create these large, or by primate standards, large social communities.
Another possible factor, and this one I really like, is fire. In our early days, our ancestors ate raw foods. Their diets consisted of nuts, plants, and raw meat. It takes a lot of energy to process that food, and a lot of energy to break it all down into something the body can use. Now, have you ever had an extremely large meal only to feel tired and lethargic afterwards? That's your body consuming energy to deal with all the food you swallowed. Feed it raw food and it needs more energy. And then, along comes fire. Not only could it be used as a heat source to deal with the cold European nights, it also enabled us to do something else. Cook. We can only guess as to how the first cooked meal was discovered, most likely by accident. But once we got our taste for it, our culinary appetites were unlocked and we never looked back. The thing about cooked food is, it's broken down for us before it ever gets to our stomachs. The discovery of fire may have also coincided with our use of tools to cut animals up. Cooking meats unlocks nutrients. Cooking is simply, well, it's awesome.
When Darwin considered the question of some of the really important factors affecting humans, he had this famous quotation that man has discovered the art of making fire, by which hard and stringy roots can be rendered digestible and poisonous roots or herbs innocuous. He said, this discovery of fire, probably the greatest ever made by man, excepting language, dates from before the dawn of history.
This is Richard Wrangham, an anthropologist and primatologist at Harvard University.
If the discovery of fire was made by one of the beings that we would classify as humans, then fire didn't do very much, because we were so stable evolutionarily after that.
What Professor Wrangham is getting at here is how fire may have played into our development of larger brains. If it all happened after our brains had achieved its present size or close to its present size, then fire couldn't have played a large part. Instead, he would argue, fire and the cooking of food happened well before modern humans ever walked the earth. It started as a flicker in a distant pre-Homo sapien past.
When we eat, our metabolic rate rises. We feel tired, we feel sometimes hot, our guts are working hard.
I know mine does every Thanksgiving.
They're doing all sorts of things. They're making acid, they're making enzymes, they're preparing for the absorption, they're actually using muscular energy. And the amount of energy that you use depends on how soft the food is.
And the brain, as I mentioned earlier, requires a lot of energy. They're not cheap.
One of the fascinating stories that's been coming out of primatology recently is the notion that you can understand variation in the size of the species' brains partly by how costly they are. Brains are very costly. In the human case, more than a fifth of the food we eat goes to fuel our brains. Every fifth hamburger and more is just used to give glucose to the brain. Big brains are expensive. They're expensive for other primates too. And the only way that primates can afford them is if they have some other organ that they're not spending a lot of calories on. And in primates, you find that the species that happen to have high-quality diets, more fruit than leaves, say, have smaller guts. And the ones that have smaller guts are able to use the energy spared from having those guts into feeding their brains. So in primates, smaller guts lead to big brains. Humans have the smallest guts of all. We have the biggest brains of all. It seems as though that would be a major contributor to enabling us to fuel that organ.
And 200,000 years ago, we modern humans stepped into the spotlight ready to take on the world. And to think, about 7 million years ago, the human brain was once a third of the size it is now. You can't judge a book by its cover, nor can you judge an animal's intelligence by the size of its brain. You can call that brain discrimination. You see a small animal with a small brain, and it's obvious that you're not dealing with a rocket scientist. Now, Douglas Adams handled this brilliantly in A Hitchhiker's Guide to the Galaxy. In the book, the mice were the brilliant ones. The Earth was built by them as a giant computer to answer the meaning of life. The joke was on us, silly apes. Adams could just as easily have used crows. Crow brains are different than ours, our last common ancestor being roughly 300 million years ago. And since that time, we've evolved the prefrontal cortex, while crows evolved an area called the NCL. Crows have shown remarkable abilities when it comes to reasoning, even abstract reasoning, both in nature and in the lab. They can use tools and recognize faces. They even have the ability to deceive. It's not about size, it's about structure. Now, there have been studies that have shown that our brains, our modern human brains, have shrunk slightly in size. Now, some estimates put the area we've lost over the last, say, 20,000 years to that of a tennis ball. Now, there are a number of theories as to why, and perhaps it's because we've domesticated ourselves. The survival pressures we once faced are no longer there. So, are we getting dumber? Well, that's debatable, but it could be that the brain is becoming more specialized. Or it could be that we are outsourcing a lot of the brain's functions just as we did with our stomachs when we discovered how to cook. I use Evernote on a daily basis when putting together and researching these episodes. I refer to it as my digital brain. I have a terrible memory as it is. I need an external hard drive at times. If the reduction in brain size is due to changes in our behavior and selective pressures on its development, then I'd like to wake Jean-Baptiste Lamarck up. He's been in a deep sleep for the past 186 years, and I love nudging him in the ribs whenever something seems to support his use and disuse theory, even loosely. Wake up, John.
What? Are you saying that people are finally listening to me?
Well, not quite.
Well then, let me get back to sleep. Wake me when they do.
And that's today's show. I love producing Evolution Talk, and I hope to continue doing so for months or maybe even years. And you can help by supporting the show. Just point your browser or your smart device to evolutiontalk.com/support. And thank you ahead of time for doing so. Now, if you want to learn more about the music on today's episode, you can find all of this and more at the show's official site, evolutiontalk.com. And as always, thank you for listening to the show. And until next time, please take care of yourself.
The brain, a pulpy mass of cells and fibers, is the center of the network of fibers that make up man's nervous system. Extending upward into the skull, the spinal cord...
Evolution Talk is a Rick Coast production.